Ito diffusions again. The main kind of random function that is interesting in this course is the Ito diffusion. So let's put that together with the concept of a martingale. In other words, what does it mean for an Ito diffusion to be a martingale? Well, if we have an Ito diffusion, so let's have xt be our Ito diffusion, that means, remember, that it's something we can now write like this. ut is the drift, vt is the speed, and you're encouraged to think of this as meaning that a little increment of the process xt, say from t to t plus delta t, would be ut times the increment of time plus vt times an increment of a Brownian motion. And the increment of the Brownian motion, remember, is this little normally distributed random variable with a variance which is equal to the elapsed time, dt. Let's actually write that explicitly because that's the key to understanding whether it's a martingale or not. So this means that x t plus delta t minus xt, the increment of x from t to t plus delta t, is, now I wrote this before by just writing down that it had an approximate normal distribution, conditional on knowing things up to time t. But I'm going to write it more explicitly now in terms of ut and vt. It is ut delta t, this is what gives it its mean, plus vt times, and this is where the increment of the Brownian motion would come in. Just to remind you, I'll write it down the way I wrote it a few times ago. This has approximately the normal distribution with this mean and this variance, conditional on ft, knowing everything up to time t. Okay, well now we've got it written down this way, you can kind of see what would it take to make it a martingale. That is, what would it take for that increment, conditional on ft, to have expectation, what does this need to be for a martingale? It needs to be 0. Well, actually, what is this? If we think of it in these two terms, ut, remember, now ut is measurable with respect to ft. So that first term, its conditional expectation, is just itself. ut is supposed to be among those things you already know at time t. Plus, and here we've got this thing, the vt is also measurable with respect to ft. So it should also be known at time t, which means in terms of the conditional expectation we can treat it as a constant. So we're just left with this. And now the increment of the Brownian motion from t to t plus delta t, that's independent of ft, it's independent of all previous time intervals. So the conditional expectation is the same as the unconditional expectation, which is 0. So we end up with just the first term. So to be a martingale requires this to be 0, and it turns out that this is essentially this. I should say approximately equal to here if I'm being careful. But that points you to a very simple answer to the original question. What does it take to make an Ito diffusion be a martingale? All it takes is for the drift ut to be 0. So the process is a martingale. That's exactly equivalent to the process ut being identically 0. So this is a really simple thing. Among all the Ito diffusions, the ones that are martingales are just the ones with 0 drift. Okay, let's just explore that a bit more. If the drift is 0, so suppose now that we've got a martingale Ito diffusion, something that is both, we could write that in this form. Just this, but without the ut term, because the ut is 0. Or if we want to write that down more explicitly, we can write it as a stochastic integral. This just means this. So another way of saying what it takes for an Ito diffusion to be a martingale is that it must be a stochastic integral. So the martingale Ito diffusions are these stochastic integrals. So the processes that are made like this by taking a stochastic integral with respect to a Brownian motion, I should say stochastic integrals with respect to a Brownian motion as the integrator, things like this, they are martingales, and they are exactly the martingale Ito diffusions. In particular, remember the key property of martingales is that their expectation is the same at every time. So one thing we can note from this is that if we have a stochastic integral with respect to a Brownian motion, so something like that, then the mean of that random variable is always 0. Looking back to this thing, the mean of this part must be 0 because the mean of xt and x0 must always be the same. Now what about stochastic integrals where the integrator is not a Brownian motion? Well, let's say it's something x which is a martingale Ito diffusion. We've already seen before that if you have an Ito diffusion x and you make another process out of it by doing a stochastic integral like this, so a stochastic integral with some integrand h, then you get another process y which is also an Ito diffusion. So this is one way of turning Ito diffusions into other Ito diffusions. What's the relationship with them being martingales? Well, quite simply, if the x process is also a martingale, so a martingale Ito diffusion, then the y process is as well. So yt is also a martingale Ito diffusion. And we can see that immediately because we remember that the drift of y is just h times the drift of x, and the speed of y is just h times the speed of x. So if x has 0 drift, then y has 0 drift as well. Both the drift and the speed get multiplied by h when you do this. So for the case of x being a martingale, the drift of x is 0, therefore the drift of y is 0 as well. There's a special name for this. I didn't mention it until now, but now seems the appropriate time to mention it. Yt is called a martingale transform of x. It's called that because it's like if x was a martingale, which of course it doesn't have to be just to write down the stochastic integral, but if it is, then y is a martingale too, so this is a method for turning martingales into other martingales. And this is actually quite an important process to us. It's one that we're going to be relying on a lot in financial modelling. So just to give you a preview of what's in the later part of the course, the second half after the break, this kind of relationship would exist if you were thinking of the x process as being something like a price in a financial market and h as being a quantity of something, because then what we've got is, well, let's indeed write it like this. This is the stochastic integral. If I write it in differential form, I get dyt is just ht times dxt, which is very suggestive of all that's going on here, right? An increment of y is just the corresponding increment of x multiplied by h. So if you have a stock market in which the change in the price of something, price of a stock, is dxt over some increment of time delta t, and the quantity of that stock that you owned during that period was h, well then the amount of money that you've gained or lost is dy, given like so. So this gives you the relationship between the value of holding of a stock, the quantity of it that you hold, and the change in its price over a period. You've probably also noticed that that's a lot like the things I was just saying in the previous video about gambling. Essentially the same idea holds there, that you have a process xt that goes up or down, telling you how the underlying gambling process is performing, wins and losses, and then you get to multiply those increments up by the size of your bet, which then gives you the change in the actual amount of money you have.